Hello and welcome to Database Management Systems. I'm Chavita Christie, and in this video, I'm going to explain to you query optimization through equivalence rules. In my previous video, I've already explained all the rules from rule number 1 to 8. And in this video, I'm first going to begin with those remaining rules, which are about 4 rules. Once I'm done with that, then I'll explain what is query optimization. So let's begin. So rule number 9 says that set operations that are union and intersection, they are both commutative, which means if you do E1 union E2, where E1 and E2 both are tables, you can also do E2 union E1, giving you the same result. And similarly, if you do E1 intersection E2, you can also do E2 intersection E1, giving you the same result. But remember and note that set difference is not commutative. Even in any type of mathematics you study, the subtraction is never commutative. So only union and intersection are commutative, but set difference is not commutative. The next rule, which is rule number 10, is that union and intersection are associative. Associativity, once again, I'd like to remind you, involves the placement of brackets, which allows us to decide which operation happens first and which operation happens next. So in this case, first we are going to see about union. So I have 3 tables, E1, E2, and E3, and I'm taking a union between them. So when I'm doing E1 union E2 first, and then taking a union of this result with E3, I can get the same result if I take E2 union E3 first and then perform the union of that result with E1. This is also true for intersection, which means if I do E1 intersection E2 first, and then the result of this, I perform intersection with E3. This is the same as doing E2 intersection E3. The result of that would be then performed. The result of that, then I can do an intersection with E1. So this is known as associativity of union and intersection. And of course, once again, set difference is not associated. Now, the selection operation, it distributes over the union and intersection and set difference operations in this manner. So I'm only giving you an example of set difference, but you can distribute it over union and intersection, which I've explained later on. Now here you can see there is a sigma p condition. P is the condition on which my select statement needs to be applied. And there are 2 tables, E1 and E2. And I'm doing a set difference between them. So I'm doing E1 minus E2 and then applying the select condition. Now I can distribute the select condition for each table individually by writing sigma p to E1, and then from there I can subtract sigma p to E2. So the select condition can be distributed. Similarly, the preceding equivalence with minus replaced with either union or intersection also holds, which means I can do the same thing if it was instead of E1 minus E2, if it was even union E2 or even intersection E2, I can still distribute the select operation. And you can see next what you have is sigma p E1 minus E2. It's the same as before, but this time on the right-hand side, the sigma condition has been applied only to E1 and not to E2. This can be done only if you do not have any columns of E2 present in P, which means the condition which is being applied on E1 minus E2, it uses only the columns that are present in E1 and not in E2, which means you don't need to apply the condition on E2 at all. So in this case, you can apply it only on E1 and then subtract E2 from it. Now let's see the next one. Next one is number 12. This says that the projection operation can also distribute over the union operation. So you can see here there is pi L, which is the attribute I want to take, a list of attributes, not one attribute, but a list of columns. And I've done E1 union E2. And from there, I'm getting some list of columns afterwards, which I want to display. So also I can do it in this manner. I can do pi L on E1 and pi L on E2. And after fetching those columns, I can perform a union. This is provided that the columns in L are present in E1 also and present in E2 also. Then I can perform it in this manner. So I can distribute a pi operation over a union operation. So that's it for all the rules. We've seen 12 of them. If you need a quick revision, you can go through them once again. I have linked the previous video down below where I have explained the eight other rules. Now we are going to see how to use these rules in practice. So we are going to see query transformation through optimization. This is where we convert one query into another query by applying one or more of these 12 rules. So for that, I'm going to use, first of all, this database, which contains three tables: instructor, teachers, and course. The instructor table contains the columns ID, name, department name, and salary. Teachers table contains columns ID, course ID, section ID, semester, and year. And the course table contains columns course ID, title, department name, and credits. Now in this, you can see that whenever I want to take a natural join, I can form a relation between instructor and course, which means I can tell which instructor is teaching which course. I can give all the details about that course and all the details about the instructor by using the teachers table. The teachers table combines instructor through the ID and the course through the course ID. So that is how these three tables are, and we are going to write a query for this question, that is query to fetch the names of instructors from music department and the titles of courses they taught in 2009. So we are given three things: the year 2009, and we are also given actually two things. We are given the year 2009 and the department music. What we need to fetch is names of instructors and titles of the courses. So the query can be written like this in relational algebra. You can see here in the query, what I have done is, first of all, we always start reading such queries from inside. So that means I have to read it from right here, from inside the brackets. So the first inner bracket says that I'm going to fetch the course ID and title from course. Now, why am I fetching the title? Because my question right here says that I need to get the title of courses. So that's why I'm fetching the title column. And then I'm also fetching the course ID column because I want to perform a natural join with teachers. And the only column that is common between course and teachers is course ID. So I have to take course ID to perform the natural join. Once I get this, I'm performing a natural join with teachers, as you can see. Once I've done the natural join with teachers, I'm also doing a natural join with instructor. And that's when this big bracket is closing. And after doing that, I am doing a sigma condition. In the sigma condition, I'm mentioning the two conditions that are given. One is that the year should be 2009. And the second condition is that the department name should be music. So those two conditions have been applied with the and or conjunction operation between the two. And after fetching all this data, then I'm applying the project operation. So the project operation is where I can finally get all the columns, the resulting columns that I require. So in this case, the resulting columns that I require are names of instructors and the titles of the courses. So those two columns I have removed. So this is a very, I would say, a fairly simple query. Now using this query, we are going to optimize it and transform it using all those 12 rules that we studied before. So let's do that. This is the query. Now notice what I've done here. I have just changed little bit in the query. You can see in the end, the upper query is having about 4 brackets and the lower query right here is having only 3 brackets. And there's one extra bracket before instructor, which was not there earlier. And there's one bracket after teachers. So what exactly have I done? If you look at it, what I have done is I have performed a natural join between instructor and teachers. They are together in one bracket, and then taken a natural join of the result with course ID and title of course. That's what I've done. And that's the only difference. In the previous query, I did natural join between teachers and course first, and then I did a natural join of the result with instructor. So you can guess which rule was applied. This is rule 6, which says that natural join operations are associative. I can change the bracket, I can change the order of brackets, and that's exactly what I have done here. Even natural join E2 first, and then result of that with E3 is equivalent to performing E2 natural join E3 and result of that with E1. So that's exactly what I've done, and this is what my query looks like now. Now let's proceed further. We can still transform it. So next what I'm doing is, you can see it right here. Now I've reduced I've reduced some more brackets. So you can see here in the upper query, there were 3 brackets after course. Now there are only 2 brackets after course. So what exactly is it that I have done? So it's very simple. You can see here what is happening. First of all, from course, I have taken out course ID and title. That remains as it is. But then you notice that there's a bracket. There are 2 brackets after teachers, right? There are 2 brackets after teachers. And there are 2 brackets before sigma condition, which was not there earlier. Before sigma, there was only 1 bracket. Now there are 2. So what I have done is, previously in the top query, my sigma condition was applied on all 3 tables. So first I took a natural join of all 3 tables, and then I applied the sigma condition. But down in this query, what I've done is applied the sigma condition only on instructor and teachers. The reason for this being, instructor contains department name column and teachers contains year column. So I do not need the course table in order to perform the sigma. So first I'm applying sigma on instructor natural join teachers and pi on course, and then taking a natural join. So it's just a different order of operations. And here the rule that I've applied is rule 7a, which says that the selection operation distributes over theta join operation under 2 conditions, and we have used the condition which is A. So the part A of that rule, where you can see that all the attributes which are present in the sigma condition, they belong to only one of the tables. In our case, they belong out of 3. They belong to only 2 of the tables, and that's why I can separate that sigma from course and apply it only individually to instructor and teachers. Okay, now let's proceed. So this is my query right now. I can still transform it. And I'm going to perform a transformation only in this red area that you can see. So let's just take that red area out. That red area, I have taken it out, and you can notice I've already done some transformation. The transformation that I've done is, instead of the conjunction, I have applied 2 sigma conditions. So first I've applied sigma year equal to 2009, and then to the result of that, I have applied sigma depth name equal to music, which is the same as saying sigma depth name equal to music and year equal to 2009. Now I can transform this into this. So what is happening in this case? In this case, I have done sigma depth name equal to music from instructor and applied the sigma year equal to 2009 only on teachers. Now, why would I do that? Because the department name column belongs to only instructor. Department name is not present in teachers. And the year is only present in teachers, but it's not present in instructor. So I can still make it, individual sigma operation. So I have individualized. You can see now depth name condition is applied only to instructor, and the year condition is applied only to teachers. Now, once this is ready, I can now modify my previous query from where I modified only a part, the red part. I can change that now. So the query would look like this now. You can see here in the query, there is a pi name comma title, which remains as it is. But you can see there are separate conditions applied to each and every table. For example, to the course table, I have applied a pi condition where I'm taking course ID and title from the course. And to the teachers table, I have applied the year equal to 2009 condition. So the year equal to 2009 condition is applied only to teachers. And the depth name equal to music is applied only to instructor. And once I've done all this, I've taken a natural join between all three tables after applying pi and sigma. And then from the whole result, I can fetch the name and title, which is what I need to display. So this was my original query, which of course I have transformed now, but I would like to show you what this original query is in terms of a tree. So in the beginning of query processing videos, when I started this series, I explained that an algebra query can be converted into a parse tree or an evaluation plan tree. So this is that type of a tree. Now you can see that I've converted it into a tree. Now how can I convert it into a tree? So first of all, you can see, read your query, and in the query what I have is the first operation being performed is the innermost bracket, and the innermost bracket says pi course ID comma title from course. So that is what I've kept here in my tree. You can see there is a course table. From the course table, I have applied the pi operation with course ID and title. So I've taken that. After that, my query says to perform a natural join of this with teachers. So I've shown that also here, natural join of course with teachers, and then perform a natural join of this with instructor. So once again, there is another natural join symbol with instructor. So that is also present. And after that, I performed sigma operation, where I've taken depth name equal to music and year equal to 2009. Both of those are present right here, you can see. And then over it, I have taken the pi operation. So the pi operation is fetching for me the name and title columns from this whole query that we have done so far. So this is what the tree looks like for my original query. This is the original query without any transformations. Now let's see what the tree looks like for this query. This is the query that we so meticulously transformed into this form. And you can see here I'm applying all the operations individually on the tables and then taking a natural join. Let's see what the tree looks like here. So the tree looks like this. First, you can see in the bottommost part, in the previous query, in the bottommost part, only course was there at the lowest level. But in this case, the course, teachers, and instructor, all three tables are present in the lowest level. And then I'm applying all the conditions to them. So to instructor, because I have individually applied depth name equal to music to instructor, I can apply that condition directly to instructor. To teachers, I have applied condition sigma year equal to 2009, which also I've individually applied. Then I can take a natural join between these two. And with that, I can also apply the pi condition to course, which you can see here, course and then pi condition with course ID and title. And then I can take a natural join of course with the result of instructor natural join teachers. And once that natural join is taken, I simply have to do pi course comma name, comma, title. So this is what my tree looks like. Now you can see this is a much more balanced tree than what we saw earlier. Let me show you the comparison of the two. So this is the transformed tree, which you can see here. And what you can see on top, this one is the initial tree. Now, even you can notice some, even though you haven't seen a parse tree before, although I showed you a very small one, but even though you haven't seen it, you can notice the differences, right? Check how many levels are there in the initial tree. Let's count the number of levels in each of these trees. So in my initial tree, I can have pi, which is one level, sigma level 2, natural join level 3, another natural join level 4. Pi operation is level 5 and course is level 6. So there are 6 levels in my initial tree. In my transformed tree, however, if I count, then pi is the first pi root is level 1, then natural join level 2, natural join with pi is level 3, sigma, 2 sigma operations level 4, and all the tables are level 5. So there is one less level in the transformed tree. And this helps us in many ways. If you watched, I think, the second video on query processing, which I've linked down below, in that video, I've explained a technique called pipelining for processing queries where multiple operations can be simultaneously done. And if you see in the transformed tree, this is easier because while I'm performing instructor and teaches while I'm doing their sigma operations, I can at the same time run the pi operation on course because I don't have to wait for instructor and teachers to finish the sigma in order to perform pi on course. But if you see the initial tree, the first thing that I can do is perform pi on course. I can't do anything with instructor and teachers till pi operation on course is finished. Only then I can take a natural join with teachers. And till that is going on, I cannot do anything with instructor. I can only take natural join with instructor once this first natural join is over. And so this query is going to take a longer time, although it's producing the same result and it is the same query. But making these transformations through these 12 rules, it changes a lot in terms of execution and processing of a query. So this is how you can optimize your queries using the query equivalence rules. And that's it for this video. I'll see you in the next one. Thank you for watching.